My name's Beck, and over the past year, I've been designing a long range RC plane. I initially wanted to design a 3D printed VTOL drone, but I realized pretty quickly that due to budget constraints and technical complications, that my best option for the longest flight time possible would be a fixed wing RC plane. So this design supports long-range flight times of up to 2 hours with the 10,000 milliamp four-cell battery. The battery I chose is a four-cell 10,000 milliamp LiPo, and its large capacity combined with the light foam frame is what enables me to achieve such long flight times of around 2 hours. And it's connected to a Y splitter XT60 cable, which powers the power module and the ESC. Balancing weight and battery capacity is important, and this battery is the perfect combination of energy density and weight. So, in order to actually power the flight controller during flight, I had to get a power module which essentially steps down the voltage from the battery and gives the flight controller a stable 5 volts. Anything more than that, and the flight controller would get fried, but any less, and the servos or telemetry modules may not work properly. The electronic speed controller I used is rated for 40 to 60 volts, which is necessary to supply enough power to the motor, and also the main out VCC rail on my flight controller, which powers the servos. Its input is connected to the Y splitter XT60 cord, and its main output goes to the motor, while a secondary 3-pin 5-volt output is connected to the flight controller's main out rail. The servos are powered through the rail as the flight controller does not supply 5 volts. The flight controller is a 2.4.8 Pixhawk and it supports autonomous missions. This means that the drone has a built in autopilot, which I can command from the ground station to perform predetermined flight maneuvers. The Pixhawk is mounted with Velcro on the upper shelf in the fuselage, which allows for secure storage and easy maintenance. It's powered by the 6-pin 5-volt output from the power module. It also has a built in GPS and 6-axis compass. So the only external telemetry module I needed was the airspeed sensor. So my design uses a single motor that's screwed into a small piece of plywood on the back of the fuselage, and I chose a Sunny Sky 1100 kilovolt motor and a 11 by 7-inch carbon fiber propeller. Because of this, it's extremely loud even when at half throttle. Because there's only one motor, though, there's nothing to cancel out the torque that the motor generates, and it causes the plane to veer slightly to the left during takeoff. My design uses three servos, one on each wing and one on the rear elevator, all mounted on the underside of the frame. So they rotate about 150 degrees, and the changes are almost instant. The servo wires and extensions are routed through the internal carbon fiber rods connecting the wings. The servo horns are screwed into each flap and are connected by a small carbon fiber rod to the servo's arm. So the transmitter is a Radio Master Pocket, which has 16 channels and supports a range of up to 10 kilometers with its internal antenna. And the transmitter talks to the receiver, which communicates the changes in controller input to the flight controller, which results in the correct servo or motor adjustments. So setting up the transmitter and receiver was a little difficult because some adjustments I made to the controller inputs conflicted with the ones that I made on the software that I used to actually bind the transmitter and receiver. I chose to make my own landing gear because I didn't feel like spending any more money on buying landing gear. And for my first test flight, I hand launched the plane, but due to the center of gravity being too close to the nose, the plane dipped after release and crashed. So after doing some research, I decided to make landing gear because it'll give the plane a little more time to pick up speed and generate enough lift. The landing gear is made out of just wooden dowels and metal dowels and furniture wheels I got from Ace Hardware. For the airframe, I purchased a pre-cut EPO foam airframe for around $200 because my initial 3D printed design was too heavy for the motor to produce enough thrust for takeoff, and also some of the parts got warped. And so I put two coats of spray paint and two coats of polyurethane clear coat to protect the foam from the sun. And this airframe also included carbon fiber rods, which are to help with the structural support and decrease the effects of turbulence on the wings during flight. In addition to this, I also put pieces of 3M flexible tape all along each flap on the wings in order to support the foam connection. With this modular design, I'm able to detach the rear elevator and stabilizer fins from the wings and the wings from the fuel silage via the screws. This makes it a little easier to transport, but I'm not able to detach the wings from each other, so I can't change the 1800 millimeter wingspan. So on the software side of things, all I had to do was set up the controls and telemetry modules in a free open source flight controller programmer called Mission Planner. And this is where I configured all the different RC channels to control the servos and motor. I also had to learn basic RF communication protocols in order to pick the right components that I knew were going to be compatible and to just set up the different channels and the inputs that controlled them. In the future, my next steps are to test flight a couple more times so I can get a baseline of the trims that I need to change on the servos. And once I have this, I can set up the autopilot, which means that it can carry out autonomous missions without me needing to control the servos or motor during flight. And I'm also going to install a camera that I purchased, but in order to actually transmit what the camera is seeing, I have to get a new VTX board, which will connect to the um, VRX receiver that I have for my ground station.